All right, good afternoon. Welcome to the second class for this course. Last week we spent basically most of the time introducing our first mixed model, and that was predominantly in the context of the lizard data set, and then we also applied it to the Captopril data set, which is only like a situation where you have paired observations. But the main message from last week is that the moment you have clustered data, hierarchically structured data, longitudinal data, repeated measurements, multi-level data, however you may want to call them, you have a correlation issue. And we have seen that this correlation cannot be just avoided. So we have to deal with the correlation. We have to take that correlation into account in our modeling. If not, we will end up with wrong p-values, wrong confidence intervals, and so on. And there's many different approaches, but one of the most flexible approaches is a mixed model or a multi-level model. And as we have seen last week quite extensively, how we do that is we model variability between the clusters, and then implicitly, automatically, you also take care of the correlation structure in your data. So we will never model the correlation directly, but the correlation will be dealt with implicitly by modeling the different sources of variability in our data sets. Before we continue, are there any remaining questions with respect to what we have discussed last week? Things that were not entirely clear, or that after the class you started thinking about it and you said, well, why is this or why is that? Just let me know, give me a sign, and we can deal with your questions. Okay, if not, let's continue and move on to another data set, the growth curve data set, which will be basically the first real example of a longitudinal data set where we will have more than 2 measurements per subject. And more specifically, maybe I should turn this on, more specifically, what we are interested in, or what the researchers were interested in, is the relation between the growth of children on one hand and the height of the parents on the other hand. And then more specifically, they only looked here at girls. So they will study the growth of schoolgirls, so female children, and they will relate that to the height of the mothers. So they will not take the fathers into account. And then what they did is they took 20 schoolgirls and they measured their height at 5 different time points, when the children were 6 years old, 7 years old, 8 years old, 9 years old, and 10 years old. So you have a completely balanced data set. We have exactly 5 observations per child, and all these observations are taken at exactly the same time points. Later on, in some of the later examples, we will start to deviate from that, maybe not all these subjects will have exactly the same number of measurements, or that maybe measurements will not always be taken at exactly the same time points. But here it is completely balanced, and then the children are subdivided into 3 different groups according to the height of the mother. So you have a group of children with small mothers, and these were mothers with a height less than 155 centimeters. These are the children 1 up to 6. And then you have 2 groups of 7 children. One group with the tall mothers here. These were the mothers with a height more than 164 centimeters. And then the group in between, this is the group of the children with medium mothers. And then here we immediately see the data graphically represented. So what you see here is, again, obviously the 3 different groups. And then on the y-axis, you see the outcome, so the height of the child. And then on the x-axis, you see the age at which measurements were taken. And that's a plot a little bit similar to the plot that I have shown you last week when we talked about the Captopril data set. Only then we only had 2 observations per subject, per patient. Now we have 5 observations per child. And again, what we do is we connect the dots that belong to a single child, because that gives us much more information, and I will come back to that. And that's, I mean, maybe the first time you see this, you might say, well, this makes sense, of course. You just see the trajectory over time. But that's not what people do traditionally in statistics. If you're interested in studying the relationship between, let's say, 2 variables, y and x, what do? You make a scatter plot. We could also make a scatter plot here. And then we would just have a number of dots at each age, but you would not see which dots belong to which children. So by just connecting the dots in the scatter plot that belong to the same child, that gives us much more information about this data set. And what kind of information are we talking about then? Well, first of all, we see that the overall trend is about linear. And you might be surprised, because human beings don't grow in a linear way. If we all would continue to grow in a linear way, you would never stop growing, right? And you would become giants. That's not what's happening. The growth is very nonlinear of human beings, but of course, if the time frame at which you look at growth is sufficiently short, you don't see that nonlinear evolution. Later on in the next chapter, we will see an example where you will see nonlinear growth, but here the time frame is sufficiently short such that you get the impression that it's linear. So probably like a straight line or a linear relationship between height and age would make sense here. What we also see is that there's a lot of variability between these children at baseline. So although these children are of the same age, there's still a lot of variability between the children in terms of their height, and we're not surprised by that. I mean, if you look at children all of the same age, they're not all having the same height. So there's quite some variability. Now, that's a source of variability that we will have to deal with, but that's not of interest to us. We're not so much interested in variability at the age of 6. If that would be our interest in studying variability at the age of 6, we would not need repeated measurements. We would not need longitudinal data. All you would need is just a sample of height measurements of children at the age of 6, but you would not have to repeat your measurements at the age of 7, 8, 9, or 10. So this variability here at baseline, yes, it's there. We will have to take it into account, but that's not really what is of interest to us. What is of interest is, of course, the evolution over time. And what we do see here, and that's now the information you would miss if you do not connect the dots belonging to a single child, what we do see here is that a child starting high tends to remain high, and a child starting low tends to remain low. Well, there is, again, a name for that in statistics, and that is correlation. Because if the first observation already tells you something about what to expect for future observations, that means that there must be an association between these observations, and hence that there must be correlation between the measurements. So the whole issue about the correlation, what we talked about last week, you can see that here by just looking at this data set. The first observation is already going to be very predictive for what to expect for future observations. So we would expect in this data set to have very strong correlation for the repeated measurements within a child. How strong that correlation is yet to be seen. We will have to calculate that based on our model, and we've done that also last week, but we will come to that. So what we do see is a lot of variability between these children, just a very little variability within each of the children. I mean, if you look at one particular child, it's not a perfect straight line, but it doesn't differ much from a straight line. It's not very deviating from a straight line. So the amount of variability that you have within a child, that's very little variability. So, and that was last week the residual variability. So here in this example, we expect to have an enormous amount of variability between the clusters and only very little variability within the clusters. And then you can already guess what's going to happen? That will mean that there will be very strong correlation. Because last week we've seen if there's much variability between the clusters relative to the total variability, then that always means that there is a lot of correlation present in your data. And that is something that we can already see here in this picture. Okay, so how will we model this data set? Well, we will do the same as we did last week. So last week, if you would go back, for example, to the example with the lizard data, we started off by just a two-sample t-test where we compared males and females. Basically, that's an analysis of variance with one factor, which is the gender, okay? And then we realized, oh, we have to take into account the fact that there's clustering in the data set. And how did we deal with that? We just added a random factor, the mother effect, which is a random factor in that data set. And the same for the captopril data set. If you would go back to the captopril data set, all you basically do is you take a traditional linear model and you add a random term. You add a random effect to take into account the variability between the subjects, between the mothers, between the clusters in general. So we can do the same thing here. So let's first think about what would be a plausible model for this data set if we would just ignore the fact that there's correlation present in the data set. So yes, we know that there's 20 children with 5 observations each. So that's 100 observations. But suppose that you would be given this data set and you have these 100 observations and no one would tell you that these are repeated measurements, that some of these measurements were taken on the same children. So that would mean that you think of the data set as a data set where you have 20 children of age 6 measured, 20 other children at the age of 7 measured, and another 20 children at the age of 8 measured, and so on, and that would give you 100 different children, all with one observation. How would you then analyze this data set? Well, what are the important covariates or factors that you want to take into account? Definitely age, because that's what you're interested in. You want to study how quickly the evolution is of the height as a function of the age. So you probably would put in a covariate age. Obviously, you would also want to take into account the group structure, because we have 3 different groups according to the height of the mothers. So group would be a factor that you would include in that model. And then probably the most important one would be the interaction between the age covariates and the group factor, because that interaction is really of interest to us. If you want to know whether the evolution, the rate of change as a function of age is different between the 3 different groups, you're really interested in testing whether the age effect is the same, yes or no, between the 3 different groups, and that is, in statistical terminology, that is just a classical interaction between the covariate age and the factor group. So that would be a traditional analysis of covariance model where we have height as outcome, and then we would have the covariate age, the factor group, and the age by group interaction. Of course, we do realize that there is clustering in the data set, and we have to deal with that. We already know that from last week. So what we will do is exactly the same as what we did last week. We will take this analysis of covariance model, and we will just add a random term, a random effect to take into account the variability between the children. Last week, it was the variability between the patients in the captopril data set, or the variability between the mothers. In general, it's the variability between the clusters that you take into account. So here, it's going to be the variability between the children, because your measurements, your 100 observations, come in clusters of size 5, and each cluster represents a child. Every child contributes 5 observations to that data set. So this is the model that we will be, yes?
What's the difference with ANCOVA and ANOVA?
Oh, ANCOVA analysis of covariance. ANOVA is if you have only categorical variables, factors. But here we will use age as a linear covariance, because we have seen that there seems to be evidence that there is a linear relationship between y and age, so we will use age as in a linear regression model. So at the moment you have a model where you have both factors and covariates, then traditionally people refer to these models as analysis of covariance. But it's all in terms of, it's all terminology, so don't worry too much about that terminology.
The analysis is the same.
Pardon?
The analysis is the same.
No, it's not. Because if you would put in age as a factor, you would no longer assume that there's a linear relationship between height and age. You would then, for each age, for each of the 5 ages, you would estimate an average. And that might be a nonlinear trend that you then would be estimating. So that's the difference. But now we treat age really as a traditional covariate, as in linear regression. Okay, this is the model that we will be using. Just for the moment, ignore the BI term here and just look at the part without the BIs. Then what do we see here? We see, apart from the residuals, the epsilon terms, we see 3 straight lines. Each straight line has its own intercept, and each straight line has its own slope. And that's analysis of covariance. So you have 3 groups, and for each group you fit a straight line. You assume a linear relationship between your height on one hand and the time, which is the age here. You assume a straight line, a linear relationship, and you allow each group to have its own straight line as average evolution of height as a function of age. And of course, these straight lines all have different intercepts, and the straight lines all potentially have different slopes. And of course, what is really of interest to us is testing whether these 3 slopes here are all equal to each other. Because if the 3 slopes are not equal to each other, that would tell us that the rate of change, the growth of these children, depends on the height of the mother. And that the 3 groups do not show exactly the same rate of change, the same rate of growth. So that will be our main hypothesis of interest. But of course, that would be a traditional analysis of covariance, and now we add on top of that a random term, which is the BI, and note the I here, the index I, again refers to the child, so to the cluster. So the BI represents the fact that every child has its own level. And we've seen that also in the data. You have children that are at the higher level than other children. Think of the lizards last week. Some mothers had a higher level than the other mothers. Think of the captopril data set. Not all patients had the same level. Some patients had a much higher blood pressure than other patients. So that's the variability between the clusters. So the random effect here, the BI, is the random term, and that represents variability between the children. So that's assumed to follow a normal distribution with mean 0 and with variance sigma squared child. So the sigma squared child represents then the variability between these children. And then the residuals, the error terms, the epsilon ij, are assumed normally distributed with mean 0 and with variance sigma squared residual. So again, we will be estimating these 2 variances. How to fit this model in SAS? Well, it's very similar to what we did last week. So your fixed effects, these are the beta terms. These fixed effects, you put them in the model statements of proc mixed. The random effects, you put them in the random statements in proc mixed. So you need to separate them out so that SAS knows that this random effect here, the child effect in this example, has a completely different nature than, for example, the groups, the 3 different groups. And again, that has to do with the fact that if you were to repeat your experiment, you would not have exactly the same 20 children. So you would have other children that you would observe, so that would mean other parameters BI, while if you would repeat your experiment, you would still be estimating exactly the same betas. So these betas are population parameters. The B's are not population parameters. That's the main issue. That's the main difference. So, Proc mixed. In the model statement, we have our outcome height, and then we have the covariate age, the group effect, and then, of course, the age by group interaction. That's what is going to be of most interest to us. And in the random statement, we just put the child effect that represents then the variability between the children. And then here we see the relevant SAS output, so I'm not going to show you all the output again. I'm only going to focus on the output which is most relevant for what we want to study here. So first of all, here you see the covariance parameter estimates. So these are the estimates for these two variances. And then you see the variability between the children is about 8.9. The variability, the residual variability, so the variability within the children, is only 0.7. Well, that's what we could already tell from just looking at these pictures, that there would be a lot of variability between the children and only a little bit of variability within the child. So that's confirmed here. And then here we have our fixed effects. And that's a little bit annoying that if we want to understand what is written here, that we really have to carefully look at all these estimates. So you have an intercept, you have an age effect, then you have your three groups where the last value is set equal to 0, and then you have the age by group interaction term, where again the last value is set equal to 0. And why do I say this is a little bit annoying? Because the parameters that you see here are not, or the estimates you see here are not the estimates for the betas in this model here. And that has to do with the fact that this model is over-parameterized. And you have that in each and in every software package. So this goes back, this has basically nothing to do with mixed models, but if you just fit, let's say, an analysis of variance model, a traditional analysis of variance model, where you would have y is equal to group, a group effect, where group has 3 different levels, let's say 1, 2, or 3. The traditional ANOVA model would be yij is a mean plus alpha I plus epsilon ij. So this is the overall intercept, this is the group effect, and these are the residuals. Now, this model has 4 parameters in that mean structure, but you can only estimate 3 means. You can only, at most, estimate the average in the first group, the average in the second group, and the average in the third group. So if you use 4 parameters to estimate 3 or to model 3 averages, you have 1 parameter too many. And that's why all these software packages have to put in some restriction. And there's any restriction can do, but what SAS typically does, it sets the last one equal to 0. And that's exactly what you see. So if you would fit this ANOVA model in SAS, and you would then look at your output, you would get your effects, intercept, your group effect. For that group effect, you would have 3 levels. And then, for example, your estimates would be, and I'm just going to give you a fake example, that would be 5, that would be -1, that would be 2, and that would be 0. So SAS would set the last one equal to 0, but that means that what you're estimating here has probably a different interpretation than what you would originally think it has. So the intercept would basically be the average in the third group. And the average in the first group would be 5 minus 1, so would be 4. And the average in the second group would be 5 plus 2, and that would be 7. So the way to avoid this, and that's what we will do later on, would be to say, okay, I cannot fit 4 parameters here, so let's leave out the intercept. And if you fit a model without an intercept, then you would fit a model yij is equal to alpha I plus epsilon ij, I mean, that's still the same model, because what you're doing is you're still estimating 3 normal distributions with the same variance, but with different means. But then your effects would be, and your estimates would be the following. So you would have no intercept, so only a group effect, 1, 2, 3, and your estimates would be, well, this would be 5, this would be 4, and this would be 7. And of course, you can go from this model to that one, and from that one to this one. So they're equivalent. It's just a reparameterization of the same model. That's what you're doing. And that's exactly what is now happening also here in this table. So the overall intercept that you see there is actually the intercept of the third group. So the intercept in the third group is estimated to be 83. And the intercept in the first group would be 83 minus 1.8. And the intercept in the second group would be 83 minus 0.14. And then likewise, for the slopes, for the H effects, you see the H by group interaction term, the last parameter is set equal to 0. So it means that the actual H effect, 6.24 here, is the slope in the third group. And the slope in the first group would be 6.24 minus 0.97. And the slope in the second group is 6.24 minus 0.68. So, and that's a little bit annoying, because instead of directly estimating all the intercepts and the slopes as I had written them in my model specification, what we do is we just estimate directly one of the intercepts and one of the slopes, being beta 5 and beta 6, so for the third group, and then each time contrasts between 2 intercepts and between 2 slopes. It's not difficult once you understand what is happening here, but you need to pay a little bit attention, and especially later on, we will have models with many covariates, many factors. You always need to be very careful what parameterization did you choose for your model, and how to interpret the parameters that you get out of your software. So always carefully look at this table so that you understand what all these parameters really mean and how to interpret them. Anyway, here we see then the traditional overall tests for the main effect for age, the main effect of the group, and then what is most important for us is the interaction between the age by group, which is highly significant, p-value less than 0.001, which means that the null hypothesis that beta 2 is equal to beta 4 is equal to beta 6 can be rejected at the 5% level of significance. So we can now, based on this analysis, conclude that there is evidence to believe that the rate of change is not the same in the 3 different groups. And the growth is then related to the height of the mothers. That's what we find here. So a highly significant difference between the slopes, covariance parameter estimates, we have discussed them already. And again, we can do the same kind of calculations as what we did last week. We can look at the hierarchical model and we can look at the marginal model. And we do that to understand what now is the variance structure that we're implicitly assuming for this data set, and what is the correlation structure or the covariance structure that we're assuming for this data set. So the calculations are exactly the same as what we did last week. So the hierarchical model is the following. So given your random effect, so it basically means if you pick a child with a particular BI effect, what is then the distribution for the observations of that child? Well, given BI, the observations for Y for that child would follow this distribution, or that distribution, depending on the group to which that child belongs. And the variability would then come from your residuals, because you condition on the child. So this hierarchical model here basically represents the data for a particular child. That's the model for the data of a particular child. So the only variability that you see there is that residual variability. What is now the marginal model? So that's the distribution for your y when you do not condition on your random effects, on your BI. Well, the marginal model is always a normal one. That's what we have derived last week. What is the expectation? Well, since all the random terms have mean 0, the expectation is just the fixed effects part of your model. So we have a straight line for each of the 3 groups, with each time its own intercept and each time its own slope. So that's the beauty of these linear mixed models. If you're only interested in knowing what is the average evolution in my population, take your model, your linear mixed model, leave out all the random terms and only keep the fixed effects. And then you will have your average evolution, an average evolution for each of the 3 groups. Keep this in mind, because later on, this will change. So now we still have that. If you're only interested in the average, all you need to do is take your fixed effects. The moment we will talk about mixed models for binary outcomes or for counts or nonlinear mixed models later on in this course, this will no longer be valid. And then knowing what is the average would require additional calculations. You have a question?
Why is the mean of the distribution different than the expectation when we're looking at this hierarchy? Because the mean is centered around, let's say, B1 plus BI plus B2 PJ, and then the expectation, we take into account that BI, the expectation of BI is 0.
Oh, but you mean this one is different from this one. But this one is the mean conditional on BI. That's the conditional mean. And here, this is the marginal mean, where you do not condition. Okay? What is the variance? Well, the variance of y, if you would just take your model from here and you would calculate what is the variance of y, the variance would just be the variance of the random effects plus the variance of the residuals. So the variance of y would be the sum of these 2 variance components here, the two variances. And again, if you would take 2 observations from different children, they would not be correlated. They would be independent because they have nothing in common with each other. So 2 observations from different children are independent, but if you take 2 observations from the same child, they would have that random child effect in their model in common, and that would create a correlation. And then we again have the same correlation structure as what we found last week. It's the variability between the children divided by the total variability in our outcomes. So if we do this calculation, we end up with a correlation 0.92. So yes, we already expected there to be strong correlation, and this now comes out. So, and that basically means that if you're not careful and you would ignore the correlation in your data set, you would act as if you have 100 pieces of independent information. That's not what's happening. You have 20 pieces of independent information, and within each cluster, you have 5 repeated measurements, but these 5 repeated measurements are not independent pieces of information, and that basically means that the amount of information in your total data set is much less than what you would expect to have if you have 100 completely independent subjects. And that's why p-values, standard errors, confidence intervals, everything is affected by this correlation, because the amount of information that you have present in your data set is much less than if you would have 100 independent observations. In the extreme case where this correlation would be 1, then the amount of information in these 100 observations would be exactly the same as the amount of information in 20 observations. Because if you know 1 observation, you would know the other 4 for the same chart. And that shows that there's not much information by taking repeated measurements in that data set. Okay, Just for the sake of illustration, because as I already indicated, very often we will use models with many covariates, many factors, and so on. So you often need to play around with these models to get out the hypothesis tests that are really of interest to you. And what is then often extremely convenient is that you can use contrast statements and estimate statements. In contrast statements, you specify a contrast that you want to test. Like, that's typically done if you want to compare 2 groups, or 3 groups, or 4 groups. Well, that's a comparison of groups, a comparison of parameters. That's typically done in a contrast statement. If you say, I'm interested in estimating a linear combination of some parameters, for example, together with a confidence interval, then you can most conveniently do that in an estimate statement. And these contrast and estimate statements, you can use them in proc mixed, you can use them in many other SAS procedures, so this has nothing to do, again, with mixed models or with proc mixed only, but here you see them just for the sake of illustration. So what I would like to do here now is, okay, we have now just seen, let me go back, that the slopes are not the same for the 3 groups. I now, of course, want to know where are the differences. Do the 3 groups all have separate slopes, or is it that 2 groups have similar slopes and that a 3rd group has a deviating slope? That's what I want to know. So I will now do pairwise comparisons. I want to compare the slope in group 1 with the slope in group 2, the slope in group 1 with the slope in group 3, and the slope in group 2 with the slope in group 3. I also want to estimate directly the slope in each of the 3 groups together with a confidence interval. And that's done in an estimate statement. So in the contrast statements, you see here 3 different contrast statements. You need to give them a name so that you can recognize them in the output, that you can see that you know in your output which hypothesis is tested there. So you give your contrast a name. So for example, the first is called small minus medium, and that will compare the slope in the small model group with the slope in the medium model group. So for the group by H combination, that's the first parameter minus the second parameter, and the 3rd parameter is not taken into account in calculating this linear combination. So for the 3rd parameter, I add here a 0. And then similarly, if I want to compare the slope of the 1st and the 3rd group, I just put in here 1, 0, minus 1. So it's going to be the slope in the 1st group minus the slope in the 3rd group. And then for the difference in slope between the medium and the tall model group, I use here a contrast 0, 1, minus 1. So it's the slope in the 2nd group minus the slope in the 3rd group. And then for the estimate statements, I just want to estimate the slope in each of the 3 groups. So I just put a 1 at the right location here, and I add here the option CL, which stands for confidence limit. And then you will automatically get 95% confidence intervals for these 3 parameters. Note that there is something else that changed in my syntax here compared to the original syntax that we used. And that change is here. Before I had group, age by group interaction, and now I don't have an age effect. And also, I add here the option no int. Well, this has to do with this table here. I now want to avoid that, again, I would not directly estimate the parameters of interest. So I want to avoid that I'm still using an over-parameterized model. So here, in just one way ANOVA, how to solve it would be to leave out your intercept. That's why we now add the option no int, no intercept. But what we also had was that this H effect here took over the role of the H effect in the 3rd group. So I leave out the age effect, and then my model will no longer be over-parameterized. So the intercept is left out, and the age effect is left out. In terms of model, it's still the same model. It's just a different parameterization of that same model. But it will now directly give me the parameters that I have had in mind and that I wanted to estimate. Yes?
So it will do the same, and it's just your output that is changing and is more readable than...
Yes, exactly. Yeah, exactly.
And another question, the random effect is child, and it's also put in the class as class variable.
Yes.
That's always necessary for the random effects.
Yes and no. Later on, we will start to deviate from this, but for now, yes. Because we really want to use child as a factor, like in two-way ANOVA last week, where we included the mother effect to take into account the variability between the mothers. And then it's really categorical variable, because you really want to create these groups in your data set. But we will, later on, we will see models where in this random statement, we would also put in like continuous covariates. And then you would not see them in the class statement anymore. But then they would have a different meaning. So that will come later. Yeah. Okay, so the output that we now have is the following, and look at the estimates. That's a table that is indeed much more readable to me. So I had 3 parameters for the group effect. These are the 3 intercepts. And then you have 3 parameters for the slopes, for the age by group effect, and these are the 3 slopes. And of course, again, like what we just did here, you can go from the previous table to the new table and back. So the intercept we had before was 83.12, and the age effect we had before was 6.24, because these were the intercept and the slope in the 3rd group. And then the other parameters were just in contrast between them. And then here we have the estimate, the table with parameter estimates. So this corresponds to the estimate statements that I added. So you get your 3 slopes estimated. Now, this is not new information because we already had them also here. But what is new information is this confidence interval here for each of the parameters. And then here we have the contrast statement results, the results from specifying these 3 contrasts. And then you see that there is no significant difference between the slope of the first 2 groups, but it's the 3rd group that has a significantly larger slope than the other 2 groups. And you basically also see that here the first 2 groups have slopes 5.27 and 5.57 approximately, while the 3rd group has a slope 6.25. So that's way higher than the other 2 slopes. So the fact that we had this significant difference in slopes between the 3 different groups has to do with the fact that the 3rd group grows significantly more rapidly than the first 2 groups. And the first 2 groups, there we cannot detect any significant difference. Of course, this is a small data set, so there might be differences, and that we just don't have enough power to detect them, but that's a different issue, of course, yes.
In that case, that you are comparing multiple hypotheses, you must change the p-value.
Yes, but it's not going to change your conclusion, because remember that you would do a Bonferroni correction here. The first would remain not to be significant, and the other 2 would remain to be significant. So in terms of conclusion, it's not going to change your final conclusion. But of course, you're correct. Now, that's also the reason why we always start from looking at the interaction. That's the overall test here. Testing whether there is, yes or no, a difference between the 3 groups. And it's only when this is significant that we continue to look where the differences are. Otherwise, it makes no sense to look for differences if there are no differences. But yes, you can do, of course, a multiple correction, a correction for multiple testing.
And the solution is the statement, what is in
The solution oh, the option here, that's just to get this table, the solution of the fixed effects. Otherwise, you would only get your f-tests. So if you really want to see all these parameters, which typically is the case, because we're interested in estimating these intercepts and these slopes, so we really want to see these parameters. So that's why you will always see that option added to our syntax. Okay, there's one last thing I need to discuss here, because what you now have seen is that we kind of play around with the parameterization between these models. The original model was more doing like this. The new syntax was doing something more in the flavor of this here. And that makes sense. But there's one issue that you need to be careful about. Let's go back to the original output. The age by group interaction has an F value 21. Highly significant. The new age by group combination effect has an F value 2,800. So you're doing a different test here. So you have to be careful. Don't interpret this effect here as a traditional interaction term. So what is going on here? Well, a hint of the solution can be seen here. It's a 3-degree of freedom test, while the interaction test should be a 2-degree of freedom test, because you have a factor with 3 levels and you have a covariance. So that should be a 2-degree of freedom test for the interaction. So what is happening here? Well, what is happening here is that we test whether all 3 parameters associated to the age by group combination effects are all simultaneously equal to 0. What are all these parameters? The 3 parameters associated to the age by group combination effect are the 3 slopes. So what you're testing here now is whether the 3 slopes not only are equal to each other, but also are equal to 0, which obviously makes no sense, because you can see that these children are growing, and we're not interested in testing that. You don't want to test whether there's any growth at all in these groups. You want to test whether the growth is the same for the 3 different groups. So don't be mistaken, don't be misled. It's not because you have here in the notation age multiplied by group that this is a traditional interaction test. It's not. Before, we did have a traditional interaction test because the parameters associated to the age by group combination effect, what were these 2 parameters? It was the first slope minus the third slope, and the second slope minus the third slope. Well, if these 2 are equal to 0, it just means that the 3 slopes are equal to each other. And that means a 2-degree of freedom test. So if you need to be careful in these models. And again, strictly speaking, this has nothing to do with mixed models. But the problem is that you get to see this much more often in a mixed model context, because we will have models with time effects later on, like the age effect here, many different factors, because you have multiple groups in your data set that you want to compare, and you're really interested in those parameters. And that's why you run into this problem. So it's very important to always look carefully at this table to understand what are the parameters that I have been estimating, how should I interpret these parameters, and then related to that, how should I interpret these f-tests here that we get? Because the table with the solutions tells you how to interpret these f-tests. So the big difference now is that if you use the original parameterization, the null hypothesis that you're testing is whether beta 2, beta 4, and beta 6 are all the same, While if you use the new parameterization, the null hypothesis that you're testing is whether beta 2, beta 4, and beta 6 are all equal to 0. And it's just a completely different test. And that's why you get a different result, of course, with a much higher F statistic. So it's important to look very carefully at your outputs so that you correctly interpret your estimates and your F-tests. And of course, you can go from one to the other. And that's why often in practice you will play around with that parameterization. Or you're interested in estimating intercepts and slopes, you use the second parameterization, this one, because that directly gives you the parameter estimates for the parameters of interest. If you're more interested in like doing comparisons between groups, then sometimes it's more convenient to use the first parameterization, and you just play around with these parameterizations. If you had chosen to use the second parameterization, and you then would like to test the traditional interaction, you can do it, but then you have to program it yourself. And you can do that with a contrast statement. And the contrast statement would then be contrast, you have to give it a name, interaction, for example, and then you would say group by age. It's the difference between the first and the second slope, comma, and now you specify a new contrast. The difference between the first and the third slope, semicolon. And then you would test these two hypotheses simultaneously. So then you would test whether beta 2 minus beta 4 is equal to 0, that's this one, and whether beta 2 minus beta 6 is equal to 0, simultaneously. And of course, if these two are simultaneously equal to 0, it means that this is equivalent to testing beta 2 is equal to beta 4 is equal to beta 6. And that's your traditional interaction test. But rather than programming this yourself, you can just use the different parameterization and you will get the same result. So one procedure is not better than the other, as long as you know what you're doing and that you correctly interpret the results that you get out of your run in SAS or any other software package, because all these software packages do the same thing. So don't think it's only something related to SAS. Okay, any questions about this? If not, then let's take a look again at the model that we have just fitted. So this was the model. This was our model that we just fitted. And just carefully look to this model just for one more instance. And try to keep it in mind, because I'm going to rewrite this model. And I'm going to fast forward to the rewritten version. And now it's up to you to see what has changed. So this was the model that we just fitted. And that's the rewritten version. What has changed? Parentheses. I've added here parentheses. And of course, mathematically speaking, nothing changes. But in terms of the interpretation of the model, it's a completely different interpretation. Because now look at this model here as a model that would describe the data for a single child, child I. And let's assume that child I belongs to the short mother group, so to the first group. Then the data for this particular child can be represented by this term plus beta 2 times t plus an error term. So basically what we're now saying is that this model assumes a straight line for each child. Before, the model was just an analysis of covariance model where we added a random child effect. Now we say, well, wait a minute, we can interpret this model as a linear regression model for the ith child. This is a linear regression model here, with this as intercept and beta 2 as slope. So now, from now onwards, we will treat this linear mixed model as a subject-specific linear regression model. A linear regression model which is specific to one cluster. And different children are allowed to have their own intercept. So we're assuming here, apart from the errors, of course, we're assuming here that each child can be well represented by a straight line, but each child has its own intercept. So in the first group, the intercepts are beta 1 plus bi. So if I would look graphically at this first group, I have straight lines. They're all having the same slope, beta 2, and each straight line represents a child. And the average evolution in that group, and remember, we already discussed that, the average is just the beta part. So the average evolution would be this. And that's beta 1 plus beta 2 times t. So the average slope here is beta 1. And the slope of the ith child, if this is child I, this would be a child with an intercept beta 1 plus bi. So what is bi? Bi tells you how the intercept of that child differs from the average intercept. So if you have a child with a bi equal to 0, that's a child which has an intercept which is exactly as the average, the same as the intercept, the average intercept in that group. If you would have a child with a bi which is positive, then you have a child that starts higher than the average in the group to which it belongs. And if you have a child with a bi which is negative, then it's a child that starts lower than the average intercept in the group to which it belongs. So it's still the same model. I mean, it's not by adding parentheses that suddenly mathematically you would change something, but it's the way you interpret that model. So before it was just analysis of covariance where we added a random cluster effect. And now we say, well, equally well, we can interpret that model as a linear regression model for each cluster separately, but then that cluster is allowed to have its own intercept, its subject-specific or cluster-specific intercept. Well, this model that we see here is called a random intercepts model, because these intercepts, beta 1 plus bi, are random, because the bi are random. And in the syntax, you can fit the same model with the same output by just specifying now the following random statement. So the model statement remains the same as before, but in the random statement, we now say we have random intercepts, but then, of course, we need to tell SAS what the clusters are in my data set. And then I need to add here an option, subject is child. And then SAS knows, okay, all the observations with the same value for the variable child, they belong to the same cluster. And they all should have the model, they all should be modeled by that same model, that same straight line with a subject, a child-specific intercept. So this syntax here, or the syntax that we have seen a few pages ago, that would create exactly the same output. But it's just a different interpretation of the same model. But this is an interpretation that will open many opportunities. We need that, because what we will see very soon today is that this model here, the model that we have used so far, while it intuitively makes sense to use that model, is still way too restrictive for many situations. It makes still very strong assumptions. And if we want to extend that model, this will be the way to do it, by just interpreting that model from a slightly different perspective. All right, so from now on, the mixed model can and will be interpreted as a subject-specific regression model. So that means a regression model with subject-specific regression parameters. And the model that we have just discussed here, that's called a random intercepts model. Now, why is this model still too restrictive for many practical applications? Well, just look here. We are assuming parallel profiles. That's not always going to be the case. Why should it be that children having the same, a mother of this more or less the same height, that these children would, between the ages 6 and 10, all have exactly the same slope? That's not necessarily true. That's not necessarily realistic to make that assumption. We have also calculated the variance of y. The variance of y was given by sigma squared child plus sigma squared residuals. Note that this does not depend on the age, on the time. So the amount of variability here is assumed to be the same as the amount of variability here, and is assumed to be the same as the amount of variability there. And of course, that's a consequence of the fact that we have parallel profiles. If you have parallel profiles, then your variability here is the same as here and is the same as there. But who says that this is realistic? Why should the variability between children at the age of 6 in their height be exactly the same as the variability at the age of 10? Maybe that's not realistic at all. We also did the calculation of the correlation, and we calculated that the correlation between two repeated measurements from the same child was given by this expression: variability between the children divided by the total variability. What does that mean? It means that this model assumes that the correlation between the height at age 6 and the height at age 7, this correlation, is the same as the correlation between the height at age 7 and the height at age 8. And also the same as the correlation between the height at age 8 and the height at age 9, and also the same as the correlation between the height at age 9 and the height at age 10. But also that the correlation between the height at age 6 and 7 is the same as the correlation between the height at age 6 and 10. And that's a very strong assumption. Because intuitively, wouldn't we expect that the correlation should be stronger if you have measurements close to each other in time, and that the correlation would be weaker if the time between two measurements is further away from each other? Suppose we would agree that from tomorrow morning onwards we would start an experiment, and the first thing you do when you wake up in the morning is you just measure your body weight. You do that tomorrow morning, and then, so tomorrow is Wednesday, and also you do it on Thursday, and on Friday, and Saturday, and you continue for many days, okay? And of course, these measurements are correlated because your body weight doesn't jump up and down like crazy all the time, as you all know. But if you have two body weight measurements from two neighboring days, they will be very highly correlated. But if you wait 1 month, they will be weaker in the correlation. And you know that. I mean, if you've been ill for some time, you lose body weight, and then the moment you feel healthy again, your body weight is not immediately back to normal. It takes some time to recover because things slowly evolve within a human body. Or if you had, like, you've been on a holiday and every night you had a big dinner at the hotel where you're staying, you come back from your holiday, you gained weight. The next day, that weight gain is not gone. I mean, we would hope so, but that's not what's happening. It takes some time to recover from that. And that shows that typically we would expect measurements close to each other in time to be highly correlated, measurements further away from each other to be more weakly correlated. Well, this model cannot handle that. It's just part of the model. And yes, after last week, maybe we thought the mixed model we had come up with was blue sky because it takes into account correlation by just modeling variability. But if you now start to think about what assumptions you're making in the background, then you realize that probably some of these assumptions are way too strict to be realistic. So we need to get rid of them. We need to relax these assumptions. Well, how will we do that? Well, let's first look at these first two issues here. Parallel profiles, and as a consequence, constant variability. Well, we can very easily relax that. If every subject already has a different intercept, why not also allow each subject to have its own slope? And then you might have some subjects that grow more quickly and other subjects that grow less quickly. So what we need to do is, well, I was a little bit too quick, but if you just look at the observed covariance matrix and the observed correlation matrix for the growth curves, then this is the observed covariance matrix, then you see that the variance is not constant in your data. And also the correlation, two observations close to each other show a correlation 0.96. If you have like 4 years apart, the correlation is only 0.83. So it shows that probably the model we used was not realistic for the data set at hand. So how to solve that? Well, we will allow different subjects to have their own slope. So the BI is still there from before, but I now call it B1I, because I will now have two random effects per child, an intercept and a slope. Every child will have its own intercept, B1I, and its own slope, B2I. So the B1I is the subject-specific intercept, so that still represents here how the intercept of the child differs from the average intercept in the group to which that child belongs. And then the slope, B2I, will tell you how the slope of the ith child differs from the average slope in the group to which that child belongs. So suddenly, the picture would then become like this. The average would still be beta 1 plus beta 2 times t, but a particular subject, for example, subject I here, subject I, would have an intercept beta 1 plus b1I and a slope beta 2 plus b2I. times t. So a child with a random slope which is 0, that's a child that grows at the same rate as the average in that group. If a child has a B2I which is very positive, that's a child that grows more quickly than the average in that group. And a child with a B2I which is negative, that's a child that grows less quickly than the average in that group. So that's what I said before, just reinterpreting that model as a subject-specific linear regression model will open many perspectives. Because the moment you realize that the model we used before is not just analysis of covariance with a random factor, but that this is a linear regression model for each subject with subject-specific intercepts, then it's only a small additional step to say, well, if different subjects can have their own intercepts, why can't they not have their own slope? And you just add a random slope. And why are these slopes random? Because they're subject-specific. If you randomly sample new subjects, you will randomly sample new B2I terms from a population of slopes. So the B1Is will still follow a normal distribution with mean 0. The B2Is will also follow a normal distribution with mean 0. And more specifically, we will assume that the two together, denoted by the vector, which is now a bivariate vector Bi, that this vector follows a bivariate normal distribution with mean 0 and a 2x2 covariance matrix T. And as before, the residuals still follow a normal distribution with mean 0 and variance sigma squared. And the D matrix is just a 2x2 covariance matrix, so D11 is now, in the earlier notation, D11 was sigma squared child. That was the variability in the intercepts, so the variability in the child effect. And now, because we will have two random effects per child, we will denote them by D11 and D22. So D22, that's the variability in the slopes. So if the D22 is very small, then it means that all these children more or less have the same slope. And that we're close to parallel profiles again. But if D22 would be very large, then you know that children all grow at different rates. And D12, that's the covariance between the intercepts and the slopes. And sometimes D12 really is of interest. If you want to know, I mean, suppose you're in an artificial, just let's think of a situation where you have patients with high blood pressure, you want to treat them, and of course you hope that the blood pressure gets smaller. If you want to know how quickly the blood pressure drops, whether that's related to the level where you start, then that's a question about the association between the slope and the intercept. And then you would be interested in testing whether D12 is equal to 0. Because if D12 is equal to 0, it means that your rate of change is not related to your starting value. And that your random intercept and your random slope are completely independent of each other. But if the two are hardly correlated, it means that your starting value will tell you something about how to evolve. And in some cases, that's really a key hypothesis of interest. People are really interested in that. How can we fit that model in SAS? Well, it's very easy. All we need to do is tell SAS that we already had a random intercept, we now also want to have a random coefficient for the age effect, for the time effect. So the fixed effect remains the same. The fixed effect structure, the mean structure remains the same. So the model statement, nothing changes. But what does change is in the random statements, you have your random intercept, and now you also have a random age effect. And now I can come back to your earlier question. Here you see that age is in there, in that random statement, but it's not in the class statement, because age is just a continuous covariance. And all what we do here is tell SAS that the age effect here should also get a random coefficient. Sometimes people also think that an effect or a covariate can only be fixed or random. Well, here you see that this is not the case. Age is in the model statement, so it's fixed, but it's also in the random statement, so it's also random. And that's, of course, because we want to have a fixed slope and we want to have a random slope. If you would leave it out of the model statement, you would say, on average, there's no evolution at all, but every subject has its own slope. You can do that, but then graphically, what you're assuming is that people have the following kind of evolutions. So every subject has its own slope, but on average, the slope is 0. And in many situations, that's not realistic, or you would not want to make that assumption a priori. So you can play around with this, depending on what model it is that you now want to fit, and what assumptions you want to make. Okay, so all we need to do is write in the random statement the age effect added there. We still have to tell the software what are the clusters, so that remains the same. A new option is type is UN, and that has to do with the structure of that D matrix. This D matrix, which is the covariance matrix of these two random effects, which is D11, D12, D22, D12. If you just want to estimate a general 2x2 covariance matrix, D, then you just put in here UN, and UN stands for unstructured. No special assumptions about D are made. But if, for whatever reason, you would want to fit a model where you implicitly restrict the covariance to be 0, for example. So if you really would insist on having a model where the rate of change, the slope, is completely unrelated to the intercept of a subject, you can do that. And then you set this equal to 0, but then you cannot use UN. You need to use another option. Or if, for whatever reason, you would want to restrict D11 and D22 to be equal to each other, you can do it, but it would not be option UN. You then need to have another option. If you would look in your help function in SAS, there's like maybe 30, 40 different possible options. We're not going to use them in this course, because in most of the examples, there is no reason to a priori put on special structure on that covariance matrix. I mean, no one has a direct link to God who tells you that the starting value of a subject is unrelated to the slope of that subject. So why would you want to, a priori, make the assumption that this covariance is equal to 0? So in most of the situations, you just keep that as flexible as possible, as general as possible, and you just use the UN option here. And then the G and the G core options, these are just output options. You will see it in the output. So if you don't add them here, your entries in the D matrix will just be listed in a small table. If you want to have them printed in like a 2x2 covariance matrix, then you need to add the option G. If based on that covariance matrix, you also want SAS to calculate for you the correlation matrix for the random effect, so if you would want to know what is the correlation between the random intercepts and the random slopes, then you just add the G-correl option as well. And then you will get a 2x2 correlation matrix printed out. But it's not doing something new, it's not doing something additional, it's just additional output that you get. And this is what I was referring to. So the traditional output looks like this. So in the covariance parameter estimates, before we had the variability between the clusters and the variability within the clusters, now we get 4 parameter estimates. The UN, and that refers to the UN option for D, the 1,1 element, the 2,1 element, and the 2,2 element. So this, and this. So the variability in the intercepts is 7.6. The variability in the slopes is estimated to be 0.13. And the covariance between the intercepts and the slopes is estimated to be minus 0.44. And the residual variance that we already had before, the residual variance is estimated to be 0.47. And then here you see the result of the G option. Then you see the first 3 entries here just printed in a 2x2 covariance matrix. And based on that covariance matrix, you can calculate the correlation matrix. And then you see that the correlation between the random intercepts and the random slopes is negative, minus 0.44, which is apparently known by people who are more familiar with how children grow. If a child at a particular age is exceptionally tall, it tends to grow less quickly afterwards. And if a child is at a particular age is particularly small, it tends to grow more quickly afterwards. And that's what you see here, negative correlation between the slope and the intercept. And then you still have your traditional F-tests for your fixed effect. So here you see again a summary, the variability in the intercepts, variability in the slopes, the covariance, the correlation matrix, correlation between intercepts and slopes, and then the residual variance, which is 0.47. Note that while we did not change anything to the mean structure, the fixed effects in the model, we again get different inferences. Before, with just a random intercepts model, these were our F statistics. Now, with the random intercepts and random slopes, you see different F statistics. I mean, the conclusions wouldn't change. The interaction is still highly significant here. But you see that playing around with the random structure of your data has an impact also on the inferences for your fixed effects. And we've seen that already last week, because that's exactly the same as when we first looked at the lizard data. We did not take into account the correlation, we did not take into account the random effect, and the difference between males and females was not significant. When we took into account a random effect, suddenly it was significant. So just changing the random effect structure of your data sets has an impact also on the inferences for your fixed effects. P-values will change, confidence intervals will change, and so on. All right, any questions on this? If not, I propose that we have our break now and that we then continue by looking at how the issue with the constant variance and the constant correlation and so on, how that has been solved, and if it has been solved. Because yes, we have extended the model, but what are now the implications for the assumptions we're making in the background? We have to check that. And that's what we will start with after the break. All right, so yes, we have now extended the model, but the question is, what happens to the variance structure in the model, or the variance structure that is assumed by the model, and the correlation structure that is assumed by the model? Because after all, remember, we did the extension to solve the issues that we had listed here, and now we need to check whether we indeed have solved some of the issues. So to check that, we again go through the calculations where we start from the hierarchical model and then derive from the hierarchical model what is the marginal model, because that's what tells us what is the variance structure that we're assuming and what is the covariance structure that we're assuming. So the hierarchical model is now the following one. So conditionally on the random effects, we still have a normal distribution with a mean which is a linear function of time, but then with subject-specific intercepts and subject-specific slopes, and the residual variance is basically the variance in that conditional distribution here. Since everything in that model is normal, we still have a normal distribution for the marginal density or for the marginal distribution of our outcome. The expectation will be the same as before, because the random terms have mean 0. So if you're interested in the marginal average, all these random effects disappear, and the only terms that are left are the fixed effects. So what you're assuming about the average trends in your population doesn't change, but that doesn't mean that you may not get different estimates and different inferences for the parameters, as we have seen. So your assumptions remain the same, but you will get different inferences. What is the variance? Well, the variance of y, you just plug in your model there. The fixed effects don't contribute to the calculation of the variance. And what you then get is here the variance of that sum. The random effects are assumed independent of the residuals, so that can be separated out. But of course, the variance of B1i plus B2it, that is not just the sum of the variances, because the B1i and the B2i are correlated. And that's why you get here the covariance term here, and that means that the variance is this function. And it's a complex function. But what you do see is that suddenly it's no longer constant. It's no longer assumed to remain constant throughout the observation periods. It depends on time. So the variance of your outcome is a function of time, but it's not just any function, it's a quadratic function. It's a quadratic function of time where you see that the entries in that D matrix are the coefficients in that quadratic function. So the quadratic term is the D22 element, the linear term is 2 times D12, and then D11 plus the residual variance, that's the constant term. So that's what you're assuming, whether you like it or not. So that's what you need to realize. If you use a random intercepts model, you automatically assume constant variability. If you use a model with random intercepts and random time effects, like what we had here, you then automatically assume a quadratic function over time for your variance, which may or may not be realistic. We will have to check that. What about the covariance? Well, if you have two observations from different children, they have nothing in common from these random terms. So that covariance of these two outcomes for two different children will be 0. And that's what it should be. That's also what we expect it to be, because two children have nothing in common. They're completely independent of each other. But if you take two observations from if you take two observations from the same child, so let's take two observations from child I, and the two observations are the observations J and K, and you then work out the covariance between the two outcomes, then it looks complicated, but it's just simple, quite simple calculations. Then you will see that the covariance will end up to be this here, and it's no longer constant. So the covariance is not constant, and so will the correlation not be constant. So the correlation between two repeated measurements from the same chart is this very, at first sight, complex function, but for sure what you can say is that it depends on the actual time points at which the measurements were taken. And that was the key criticism that we had, that the correlation between any two repeated measurements from the same chart was always the same, irrespective of the time points at which these measurements were taken. But again, whether this is realistic, yes or no, question mark. We will have to check that. And what you do typically is you fit your model, and then based on your model fit, you have estimates for all those parameters, and you can compare the fitted correlations with the observed correlations in your data set. That's what you typically do. And the same for the variance. So you have your fitted variance function, and you compare it to what was the variability that we have observed at each point in time during this study. And you compare the two to see whether what your model assumes is realistic and is close enough to what you see in your actual data set. So just to show that, for the growth curves, the fitted variance function of y is just d22 times t squared, 2 times that covariance times t, and then the constant term. I now plugged in here all the estimates that we had obtained, and I can then have the fitted variance function. And here what you see is the fitted covariance and the fitted correlation matrix, which I get from putting in my random statements the options V to get the covariance matrix and the V corr to get the correlation matrix. So that's the covariance and the correlation matrix based on your model fit. So that's what your model assumes. So basically, on the main diagonal for the covariance matrix, you will see those entries. So the entries that you see here, they satisfy the function that we calculated here. And then the same for the correlation matrix, that's here. And now you can compare it to the observed covariance matrix in your data set and the observed correlation matrix. And then you can see whether those are close enough to each other and whether those are close enough to each other. And of course, that's not so easy to see. So very often what we try to do is we make a plot. And here we see a plot of the variance function. So what you see here is that the observed variance function is the red curve. It's increasing and then it decreases again. And the fitted variance function, which is this function here, that's the black curve. And then you see that it's no way close to the observed variance. So it shows that, yes, my model is more flexible in the sense that it no longer assumes constant variability over time, but it's still not flexible enough to really capture the true variability structure in my data set. And actually, if I could have told you that already prior to looking at this plot here, because we've seen before that when we looked at the observed covariance, that the variance went up and then down. So we knew that the variance would show a function like this. But if we look at what we just calculated for the fitted variance function, it's this one. It's a quadratic function, and what is the quadratic term? The quadratic term is d22, and what was d22? It's the variance of the random slopes, which is positive. So this is a quadratic function with positive curvature, so it has to look like this. It can never show this negative curvature. So if you look at your data and you see that there's negative curvature in the variance function observed for your data, forget about the model that we just used, because it can never capture that. It's impossible. Next year, what we will do in a case like that is we will allow that D22 to become negative. Because we will see, okay, we need negative curvature. Well, we can get there by allowing the D22 to become negative. But then immediately you run into trouble by the interpretation of D22, because then it can no longer be the variance of the random slopes. A variance cannot be negative. But that's for next year, okay? So the bottom line is that the model is more flexible, yes, but it's definitely not flexible enough yet. So if we want to come up with a realistic model for these growth curves here, we will have to do something additional. And then what will we do? Well, I think by now you get the general idea already. The fixed effects, you use them to model the average trends. The random effects, you use them to model the whole covariance structure. So if the covariance structure is not sufficiently flexible yet, we need to throw in more random terms in that covariance structure. So one way to do it, and I'm not saying this is the only way to do it, but one possible solution would be to say, okay, let's add a quadratic random term for h squared. So basically what you then do, if I would write down the model, it would be in the first group yij is equal to beta 1 plus b1i plus beta 2 plus b2i tij plus b3i tij squared plus epsilon ij. That's what you're doing. And of course, you might say, why not add a fixed effect here also? You can do that, but if you already see that the average trend in your data is more or less linear, then you don't need the quadratic trend for the fixed effects. And then you can say, I don't need that quadratic term for the fixed part, but maybe I need it for the random part to get a more flexible model for the variance function and for the covariance structure. And if I now redo the whole calculation and I look at the new fitted covariance matrix and I compare it to the observed covariance matrix, here then you will see that we get much closer already. So it increases and it starts to decrease. And if I look at this in a picture, the red curve is the same red curve as what you had before, of course, because this was just the observed variability in the data. And then you see that your black curve goes much more closely to the shape that you had seen in the data. So that's the general strategy. These fixed effects, you use them for the average trends, for the average trends in your population, and to study and to describe these average trends. The random effects, you only need them to get this whole association structure and variance structure correct, so the whole covariance model correct. By the way, if you would again calculate what is now the marginal variance function, it's again a polynomial, but now it's of the degree 4. So if you just have random intercepts, it's a constant. If you have random intercepts and time effects, it's a quadratic function for the variance. If you have random intercepts, time effects, and time squared effects, your variance function becomes a 4-degree polynomial. If you would add here b4i t to the power 3, then your variance function would be a 6-degree polynomial. So each time the degree of the polynomial increases by 2. And if we now look at the fitted correlation matrix and the observed correlation matrix, then you will see it's not identical, but it's more or less the same structure. And again, you can make plots of that. You make a scatter plot where on your y-axis you have your fitted correlations, on the x-axis you have your observed correlations, or vice versa, and then you should get them close to each other, so the close to one line, more or less. So the bottom line is the role of the random effects is to model the variance and the association structure, period. That's the only thing that this is doing. And you need to throw in sufficient random effects to get this structure sufficiently well. And again, you will see that it affects your inferences for your fixed effect. So although you don't change the fixed effect structure, you still assume 3 straight lines on average for the 3 different groups. You will get different inferences for the parameters in that fixed structure. And you see that here, so look just at the F statistics, and they're not so drastically different anymore than what you had before, but still there are some changes, and that has only to do with the fact that this whole association structure is changing, and you need that to get your inferences for your fixed effects. So you cannot say, I only care about the average evolution, so I'm only going to model the fixed effects, and I don't care about the random effects. Well, you can do that, but then you will get wrong estimates and maybe definitely wrong inferences for those parameters. So you cannot see one without the other. You need the covariance structure to be modeled correctly in order to get correct standard errors and inferences for your fixed effects. Okay, just to conclude here, a linear mixed model is basically nothing else but a linear regression model with 2 sets of regression parameters. You can quite easily see that here you have these fixed effects, you have these random effects, so you have 2 different sets of regression parameters. Some are the fixed effects, these are our beta parameters. Some are the random effects, these are our BI parameters. The fixed effects are used to model the average trends in the population, so the average outcome. The random effects are used to model the whole covariance structure in our data sets. And a little bit of additional terminology. All the parameters in the D matrix, so the covariance matrix of these random effects here, together with the residual variance sigma squared, we call them variance components. So sometimes in the literature you will also see that people refer to this kind of models as variance components models. So there's many terminologies out there: random effects models, mixed effects models, mixed models, multi-level models, repeated measures models, longitudinal data analysis models, variance components models, and they're all basically doing the same thing. So don't get confused by just different terminologies. Just look at what is the model, and then you will see that it's all the same thing. Okay, any questions on this? Good. Okay, let's continue. And I mean, the basic model we have now seen. Okay, so what is yet to come in the next chapters is a bit more complex data structures. So in this example here, not all clusters will be of the same size. We will have a longitudinal data set, but not all clusters will be of the same size. Then we will also look at a data set where we have measurements at all different time points. So measurements would no longer be at fixed time points like in the growth curves. And then we will also look at the data set where we have more than 2 levels, but 3 levels. And then you will see that you will get random effects at different levels, because you need to take into account the association at the different levels in your data structure. So it's not a major extension, but it's still an extension of the models that we have discussed. And then we will go to models for non-continuous outcomes. Okay, the RAD data set. So this is a data set basically from actually this house. It's on a data set that was collected here in dentistry. And the context is that clinicians, it's an old data set, but clinicians have been looking for ways to treat children with severe growth retardation. So children that really do not grow quickly enough according to their age, they want to treat them. And a potential treatment would be to treat them with hormones to speed up the growth of these children. And these are, of course, very drastic treatments because it affects many different parts of human growth and the human body. And you cannot just start trying this out on some children. So what they did is, and that's about 30 years ago, they did an animal experiment with rats. And then they were interested, because this is in dentistry, they were interested in the craniofacial growth. So that's the growth of the skull, the head of the animals. And they wanted to know whether the craniofacial growth depends on the testosterone production. So what did they do? They took 50 animals, 50 rats, all males, all of the same type, Wistar rats, and they randomly assigned them to 3 different groups: a control group, which contained 15 rats, and then 2 treatment groups. And the treatment was a low or a high dose of a drug called decapeptyl, which reduces the production of the testosterone in the animals. So here it's not that they would give additional hormones to the animals. No, they reduced the hormone production in the animals, just to see what would happen with these animals. And the treatment starts at the age of 45 days, so when the animals were 45 days old. That's when the treatment started, when the animals were randomly assigned to the 3 different groups. And then they would take measurements every 10 days, starting at day 50. So first measurement is at day 50, then day 60, 70, 80, until 110. That was the last final observation. And what do they measure? Well, every 10 days, they take an X-ray picture of the skull of the animal. And here you see an example of that. And in case you would not recognize, that's the neck and that's the front side, okay? This comes on a computer screen, and the person who is taking these measurements has a special pen with which he or she can identify particular points on that picture. And here they are identified and numbered in red. So it starts here 1, 2, 3, 4, 5, all the way around until 16, 17, 18, 19. All these points have a particular meaning. I mean, I'm not a biologist, I'm not a dentist. It means nothing to me, but they told me that all these points have a meaning, and I believe them. Okay, once these points have been identified, the computer starts calculating distances between these points. Distances, but also angles between different directions. And these are all outcomes. So this is a data set where you don't have like a single outcome, but you have like 25 or 30 different outcomes measured each time. Now, of course, we will model only one outcome at a time, and the outcome that we will be looking at here would be this distance here, between 0.7 and 0.9, which is one of the more important ones for the clinicians. It's like it's the height of the skull at the front side, more or less. A side remark, strictly speaking, you would want to analyze all these outcomes simultaneously. Because yes, we can do an analysis for each outcome separately. And suppose that you see that the 3 different treatment groups show a different evolution, so that your treatment has an impact on how these animals grow. Then, of course, what you would want to know is whether that these differences are the same for all the different outcomes, or proportional for all the different outcomes. Because imagine what would happen if you treat an animal with hormones, or you would reduce the hormone production, and that would have an impact which is different in one direction than in another direction. You would then get malformations. You then would not have that they're getting less large or larger, but you would not even have only the size that is different, but that also that they start growing more in one direction than in another direction, and that you would get malformations. And that can only be detected if you would be able to analyze all these outcomes simultaneously in one big model. Well, that's about impossible. Because think about this, if you have 30 outcomes with 7 time points, that's 210 observations that you have per animal. And they're all correlated. So you would be basically estimating a 210 by 210 dimensional correlation matrix. And you have only 50 animals. So that's almost impossible to do. But yes, the research questions actually are such that this would be the ideal case to do. Nowadays, people have found solutions to deal with this. And nowadays, multivariate, because that's what we're talking about, multivariate longitudinal data analysis is possible. But that's a major additional complication over and above what we are talking about here. So we're not going to do that. We will focus on this distance here between 0.7 and 0.9. And these are the profiles. So again, a similar picture. You know now already how to read pictures like this. You have the 3 different groups, the control group, the low dose group, the high dose group. The outcome is the response in computed pixels because it's a distance calculated by the computer as a function of the age of the animal, so the time here. And then you see, well, first of all, well, again, there's many different things that you can see, but first of all, you see these animals tend to grow, but no longer in a linear way. So remember what I said before, with the growth curves, we saw linear evolutions, but that was only because we have a sufficiently short time frame. But if you now look at the longer time frame for these animals, then you see the growth is more steep at the beginning, and then it starts to slow down. So that's something we will have to deal with. I mean, the model that we had here for the growth curves, without this, of course, would not work. Linear profiles would not work. So we will have to do something about it. Maybe a quadratic term, but then you probably would also need a fixed effect for that quadratic term. So we will have to come to that. We see a lot of variability between these animals. That's not new. We also saw that with the growth curves. We see that animals starting low tend to remain low. You see that very clearly here. Animals starting high tend to remain high. So we know there's going to be correlation again. Nothing new. What else do we see? Well, we see, and that's maybe something that you may not have noticed that, but what you sometimes see is like clearly here, it goes down and then up again. While these animals are growing, how can that be? Is it that they suddenly shrink and then they have a higher value again the next time? No, this is measurement error. Because even if you would give a dentist or a clinician that same X-ray picture a second time, and then I'm not even talking about taking the picture a second time. No, you take the original picture, you give that again to the clinician, he or she would not be able to identify all these 19 dots at exactly the same location. So there is some measurement error. But that's fine, because we have residuals, right? We have a curve for each subject, a rat here in our data set, and then there is within subject variability. These are the residuals. So we can deal with that in the residuals. One last issue is that these animals were measured at day 50, 60, 70, all the way to 110, but you clearly see it here, but also for many of the other animals, that suddenly the line stops. What is going on here? I mean, this is an animal experiment, so it cannot be that the animal decided not to further participate. With patients, yes. You can ask patients to come back every week or every 2 weeks and they don't show up for whatever reason. But with animals, that's not possible because you have everything under control yourself. What happens here is that, and again, I'm not a biologist, so I cannot tell whether that's correct, but I was told that in order to be able to take that X-ray picture, they need to anesthetize the animals. They need to inject a drug so that the animal falls asleep, and then they can take that X-ray picture, and apparently that's very, very difficult. If you give a little bit too much of that product, some of the animals die. So, of course, if an animal dies, you can still take your X-ray picture. But it's not very useful to take that X-ray picture again 10 days later with the same dead animal. So if an animal dies, that's the last observation you have for that animal. And that's what's happening here. So, for example, this here was an animal that died at age 80. You may notice, you clearly see it here, there's like a small dot. That's not a piece of dust on the projector, that's an animal, which was very unfortunate to die the very first time the animal was measured. So for that animal, you would only have one observation. Here you see the actual data. So this is what we call dropouts. You start with 50 animals, you intend to measure all these animals until day 110, but some drop out, and dropout is literally dropping out from your study. At one point, the animal disappears, and here we know the reason for the disappearance, and the animal never comes back anymore. We see that we have 50 animals. 4 were unfortunate because 4 immediately died the very first time they got measured. Only 22 make it until the end of the study. This is a huge problem, dropout or missing data. Here not so much, but in general, if you have longitudinal studies and patients start to drop out from your study, that's a problem. Why? Because you never know whether the patients dropping out from your study are systematically different from the patients who stay in your study. I mean, we will come back to that probably next time or the time afterwards. But if people, suppose you work with patients and you ask them to come back every week and some don't come back, and the ones that don't come back are like the better patients, then you only get to see the worst patients. And that means you no longer have a random sample. And of course, also it can also happen in the other way around, that the worst ones stay away because they don't feel any improvement at all, and only the better ones come back, and then you may be over-optimistic in your inferences. So that is a major issue, and we will kind of not discuss that this year. Next year, there will be a whole part in the course on how to deal with missing data in a longitudinal study. There's many different techniques you can use, but that's not going to be the key issue here. The good news here is that we know the reason for dropouts. It's the animal that dies. And there is no reason to believe that dying because of the anesthesia has any relationship with the outcome that we are studying here. So let's assume that there is no real issue here. Yes, there will be less power because you have less observations, but that's the only consequence. And we will not have we will not have bias in our results if due to this dropout. All right. What model can be used for this data set? Well, we need to do what we always did before. We need to think first of what kind of model would we use to describe each rat separately, because that's what the linear mixed model is doing. You try to describe each rat separately by a linear regression model. Of course, the first linear regression model one thinks about is a straight line. That's the most simple linear regression model. But if you look at these curves, then it's quite obvious that the straight line is not a good choice, because it is not linear. What is then the next step? A polynomial. Yes, you could try a polynomial here, but you also know if you take a polynomial, for example, a 2-degree polynomial would reach a maximum, and would start to decrease again, which is not very realistic in this case. So what we'll do is, what do you do in linear regression if you have a nonlinear relationship between y and x? Either you use polynomial terms or you use a transformation. A transformation of your x-axis. Well, we can try the same here. And what we will do is, if these curves are more like this, what we will do is we will look for a transformation of the h such that the higher points are shifted to the left more drastically than the less higher points, so that eventually we get here more or less a straight line. Well, a transformation that often works well in a case like this is a logarithmic transformation. So what we can do is we can try it out. You can plot your outcomes as a function of the logarithm of h, and then see whether the profiles look much more linear than what we see in this picture. And you can do that, and you would see pictures. It's not here in the course notes, but if you would just plot it versus log h, you would see pictures very similar to the pictures that you see here. Why is that? And again, this has nothing to do with mixed models. It just has to do with how a transformation works. What is a logarithmic transformation? This is a logarithmic transformation, okay? So for the value 1, you get 0, and then it continues. Look at these h values. They go between 50 and 110. Where is that on this plot here? It's not here. It doesn't fit on this blackboard. It doesn't fit here within in this room. I would have to go to the next room to get to the h frame 50 to 110. And how does that logarithmic function then look like? For these high values of h, it's more or less linear. So that logarithmic transformation would have no impact at all. So what you need to do is you first need to shift these h values closer to the origin so that you can take advantage of this curvature in this logarithmic function, and then you do exactly what we had in mind here. So the higher the values are, the more they would be like reduced and pushed towards the lower values. So the transformation that we will use is this one. So I will first subtract 45. So I shift all these values closer to the origin. Why 45? Well, that's the moment the randomization took place. That's like the start of my experiments. That's when my clock started running. And then my first measurement was at age 50. I also divide here by 10 to really push them all together, to shrink them. Why 10? Why not 20? 20 would also work, but 10 makes sense because we have measurements every 10 days. And then I add here a 1, and I take the logarithmic transformation. The advantage of using this transformation, and it's by far not the only one you can choose. You can choose many different transformations, but the advantage of this one is that my new time origin has really a meaning to me. T equal to 0 would correspond to h equal to 45. Because if h is 45, this is 0, I get the logarithm of 1, which is 0. And that's important because remember, when we did some of our previous analysis, you get these tables with intercepts and slopes. It's important that the parameters you're estimating, that they have a meaning to you. So my intercepts that I will be estimating, these will be the values at age 45, and that's when the experiment started, really, when the randomization took place. And this is the model that we will be using. So it's a model very similar to what you have seen for the growth curves. There's one tiny little difference. So I have a straight line for each group, of course, after taking the logarithmic transformation. So you first take the logarithmic transformation of h. So the t is these logarithmically transformed h values. You then get a straight line for each of the 3 groups. I now only include random intercepts. Can you not put in random slopes? Yes, if you think that would be necessary, but this is here for the sake of illustration, where I just restrict to random intercepts. And why is that? Because I tend to see that the amount of variability here is not really differing very much. So I know that if I want a model where the variability remains pretty much constant over time, that I can do that by just using random intercepts. Because the moment you would put in random slopes, you would immediately have that your variance starts to change over time. The one difference between this example and the growth curve data set is this. In the growth curve data set, we had 3 different intercepts. Why not 3 different intercepts here? You can do that, but it's not necessary. Why not? Well, that has to do with our transformation. Remember, I just said this particular transformation means that t equal to 0, that's corresponds to h equal to 45. So my intercept here, the average intercept in a particular group, corresponds to the average outcome at age 45. But at age 45, the animals were randomly assigned to the 3 different treatment groups. So we know by the design of this experiment that on average, these 3 different groups have to be the same at age 45, meaning at t equal to 0. So I don't need 3 different intercepts here. I can just immediately say these intercepts should be common, should be the same. And this is just by the choice of the transformation in combination with a randomized experiment. Because if you would not randomly assign your animals to the treatment groups, you would not know that the 3 different treatment groups would have to be the same on average at age 45. So this is the model. You can write that down in one big expression by just using dummy indicators, dummy variables. So I have one for the low dose group, one for the high dose group, one for the control group. And then you have one intercept term here, and then you have the 3 different slopes, where I have an intercept for the low dose group, an average slope for the low dose group, an average slope for the high dose group, an average slope for the control group, and of course, what would be really of interest to us is testing whether beta 1, beta 2, and beta 3 would all be equal to each other, because if they're equal to each other, it would mean that the treatment does not affect how these animals evolve over time, how the growth is over time. Any questions about this model? Because there's different aspects of the design and the model that you put together in order to get to this model. So beta 0 is the average response at the start of the treatment, which is independent of the treatment. Beta 1, beta 2, and beta 3 are the average time effects for each of the 3 different treatment groups. And then Bi is the subject-specific intercept, which tells you whether the animal starts higher than the overall average or lower than the overall average. And here you see the output. So first of all, you need to calculate this t, of course, this logarithmic transformation of h. Once that's calculated, you then have here your proc mixed statement, where in the model statement you just say y is treatment by time. I don't put in a time effect, because otherwise I again would have one slope and 2 contrasts for the slopes. I don't want that. I want to directly estimate the 3 slopes for the 3 different groups. I don't have a treatment effect. Why not? Because I don't want 3 different intercepts. I only need 1 common intercept. In the random statements, we have just a random intercept, where the subject now is the rat here. And I know, because I took this parameterization, that the f-test that I will get for the treatment by time combination effect would test whether the 3 slopes are equal to 0. That's not relevant to me. What I want to test is the traditional interaction term. And so if I want that, I can do that by specifying the contrast statement myself. Alternatively, I could switch to the other parameterization, and then I would put here in the model statement y is time and treatment by time, and then the treatment by time would be the traditional classical interaction term, but then I would not get the parameters estimated as I wrote them in my model specification here, so I would then have these contrasts again. So I therefore prefer to use this parameterization, but then I have to add a contrast statement additionally to the proc mixed syntax. So here you would see then the results. So this is the random intercept variability, 3.5. The residual variability is 1.44. So again, you see much more variability between the rats than within the rats. And then for the solution for the fixed effects, you see your overall intercept, which is 68. This is the common intercept for the 3 different groups. And then for each of the 3 different treatment groups, you have a different slope. So in the control group, it's 7.3. In the high dose group, it's 6.8. In the low dose group, it's 7.5. And of course, we want to know whether these slopes are equal to each other, and that's why we need a contrast statement, which is indeed a 2-degree of freedom test. And then you will see that there is no evidence that the slopes, the average slopes in the 3 different treatment groups would be different from each other, p-value 0.10. And again, note that if you had been not very careful and you would have just looked at the t by treatment combination term, you would probably have believed that there's a very significant interaction. There is not. This here tests whether the 3 slopes are equal to 0, while the interaction term here is testing whether the 3 slopes are equal to each other. And that's something else. Of course, the slopes are not equal to 0. The animals are growing. but the three groups can have the same growth. And that's what we see here. Okay, any questions about this example, this data set? Yes. Yeah, yeah. That's the variance of the random intercepts, and these were the BIs. Yeah, yeah. Any other questions? So, and again, I mean, you see here the if you would calculate the correlation within an animal, it would be 3.56 divided by 3.56 plus 1.44, which is about 5. So you would have very high correlation again. And that, of course, raises the issue. I mean, and we have looked into that. That's maybe also interesting to mention. I mean, in a case like that, where you see now that the animals die, well, there's a risk of dying each time you take a measurement. So the question now is, if you see such a high correlation between repeated measurements, would it not be better if they would, let's say, do a similar experiment in the future? Would it not be better to plan less observations per animal, reducing the risk that many animals drop out? Because taking many additional observations, if they're so highly correlated, adds little information to your data sets. So there is this interplay that you need to try to find a good balance between taking enough repeated measurements per animal to have enough information for your inferences of interest, knowing that at one point adding more repeated measurements probably doesn't add much to the power or the efficiency of your study, because all these measurements are correlated, and also knowing that if you take too many measurements, there's much higher risk that many animals would drop out. So even if you would say, I still want to study how these animals grow between the ages of 50 days and 110 days, maybe instead of taking 7 measurements per animal, maybe it's better to take only 3 measurements per animal. And many less animals would drop out, and you would not lose much because the measurements are highly correlated. So from a design of experiments perspective, this is kind of interesting that in the design stage, you already take into account the risk for dropout. And that has been done, but that's beyond this course. All right, no further questions on this. Let me introduce this data set, and then next week we will start from this, because this is a data set that takes a little bit of time to introduce before we even get to start modeling the data. Here, everything is normal. In this building, don't worry. It's over. Okay, what is this about? But it's far away from here. No. Okay, what is this about? So this is an example, a data set that has been described quite extensively in the medical literature, but also in the statistical literature. And it's about prostate cancer. And clinicians apparently for quite some time have been looking for easy ways to detect prostate cancer as early as possible, because apparently prostate cancer it moves around. Apparently, prostate cancer is a type of cancer that can develop for quite some time before you start noticing that. And people have shown that sometimes it takes like 5, even to up to 7 years before, in between the start of the development of the cancer and the moment that it gets detected. So by then it may be too late to still treat these patients. So they have been looking for easy ways to detect prostate cancer as early as possible. And initially they were thinking about using PSA. And PSA stands for prostate-specific antigen, which is an enzyme that you can quite easily measure in the blood of the subject. And PSA is known to be proportional to the amount of prostate tissue. So if there's more tissue, PSA will be high. That's the idea. So the idea is then, if cancer is developing, there will be more tissue, and therefore PSA will be high. However, it turns out that you can also have patients with what is called benign prostatic hyperplasia, BPH. And BPH is a situation where there's also more tissue, but it's not cancer, it's benign. So, and of course, if these patients have more tissue, they also have a higher value of PSA. So it basically means that if you would just screen patients and you would use a high PSA value as an indication for cancer, you would have many false positives. You would tell people that probably they're having cancer, while that's not the case at all, while they have maybe only BPH, which is less harmful for the patient. So then for some time they believed, okay, maybe PSA is not a good idea to use as a biomarker to screen patients. Later on, clinicians themselves hypothesized that maybe PSA would be useful, but that you would have to look at longitudinal profiles. And the idea was that in benign prostatic hyperplasia cases, the PSA value increases, but very slowly. While in cancer cases, you almost have like an exponential increase in the PSA. So the idea would be, if you follow up on people and you monitor PSA, let's say every year or every 2 years, and you see the PSA gradually increasing, that's probably not very dramatic. But if you suddenly see an immediate, very steep increase, that this would be an indication for cancer. Now, suppose you would want to set up, that was just a hypothesis. That was just clinicians who hypothesized this. Suppose you would want to set up an experiment to study this. What would you have to do? You would have to study with you would have to start with a large group of males, sufficiently young, and you would have to follow them up over time. And maybe every year or every 2 years, you would have to measure PSA. And hopefully for you and for your study, many would get cancer. Because if no one gets cancer, you would not be able to see how PSA evolves in cancer patients. So you would have to wait for a very long time, maybe 20 years, 30 years. So by the end, or by the time that you can start drawing your conclusions, probably no one is still interested in your conclusions, because it's likely that 30 years from today, they have more efficient ways to detect cancer, this type of cancer, than by just you looking at PSA. So no one would set up a study like this. So what have they done here? In Baltimore, so this BLSA stands for Baltimore Longitudinal Study on Aging. That's a big study that started in the late 50s of the previous century, and it's still ongoing, with volunteers, of course, not the same volunteers. It's constantly renewing the people, okay? but with volunteers, and these people are asked to come back to Baltimore approximately every 2 years, and each time they go back, they stay 3 days in the hospital. They have a campus there just for this study. That's a campus related to the Johns Hopkins University, so just for this study, people stay there for 3 days, and during these 3 days, they take whatever kind of measures that you can think of or dream of. They have everything. They take hearing tests, they do exercise tests, everything they measure. They keep urine samples, blood samples, everything you can dream of, they have it there. And so you ask people to come back approximately every 2 years. But that's, of course, that implies that people will not come back always at exactly the same time points. You will see that in the data. Some people come back after a little bit more than 1 year, others stay away for many years and suddenly they show up again. So it's highly unbalanced. People basically come and go whenever they like. And that's the first time we see a data set like this. But that happens all the time. If you have more than epidemiological study, that happens all the time. Now, why am I saying this about the study, and how does that relate to the prostate data story? If they had started following up patients since the late 50s, subjects, of course, some of these people started to develop prostate cancer. And some of these people, it was at one point in time that it was just detected that these people had prostate cancer. So what they did is they said, okay, we know that we have a number of cancer cases in our cohort that we are following. And likewise, they also had a number of patients with what was called benign prostatic hyperplasia, this BPH. So why not take these people from this big study, take them out of the study, take also some control patients who had no prostate disease at all, and let's see how their PSA value has evolved in the history that we have been following up on these patients. So you basically go back in time. So if a patient at one point is diagnosed with cancer, prostate cancer, you take that patient and you then look in your database over, let's say, the 10 or 15 or 20 years that you have been following this patient, what was the PSA value of that patient in that whole history? And can we now see that, yes, indeed, there was a very steep increase in the PSA value. And likewise for people with benign prostatic hyperplasia and for some control patients. And control patients are patients who needed an enough number of repeated measurements, who needed to have very extensive medical examinations to be sure that there was no prostate disease at all, yet. And the follow-up time had to be already long enough for these control patients. There was only one problem. They did this like in the late 80s, 90s, when they first collected the data from the big study to detect, to see how the evolution of PSA relation to prostate cancer. If there was a patient who was diagnosed with prostate cancer, let's say in 1970, and who had been followed for, let's say, 20 years, you then have to go back 20 years in time, so that's like 1950, like the very beginning when the cohort started. At that point in time, PSA was not known yet. So they didn't have PSA for these patients. Fortunately, what they had were the blood samples, because I told you that they keep blood samples, and they freeze them. So they have these freezers with urine samples and blood samples. So what they could do is they could go back to these freezers, take out these blood samples, and still measure the PSA, and then you have values for PSA that date back in time to moments where PSA was not yet known. So it's a very clever way of trying to solve this whole issue, but basically it means what they call that they have a retrospective you go back in time. Case control study, because you take cases, cancer patients, and control patients, based on frozen serum samples. Because they didn't have the data in their database, they had to take these blood samples and then measure PSA based on these blood samples. And they did this for 14 local cancer cases, 4 metastatic cancer cases, 20 benign prostatic hyperplasia cases, and then 16 controls. And once again, you might wonder why only 16 controls, because they have by now thousands of people in their database. Why only 16 controls when they did this study? Well, again, because first of all, controls needed to have enough repeated measurements so that you can study trends. They needed to have a long enough follow-up time, also to be able to go back long enough in time. And also these people were given very extensive medical examination to make sure that they didn't have prostate disease yet. I cannot do that for a large group. Moreover, and that's an additional complication, they wanted to select these people such that they would have more or less the same age. Why? Because PSA is known to be age-related. So if you study PSA and you want to compare PSA between these 4 groups, if any differences are observed, you want to make sure that these differences are not just purely age effects. So they wanted to get these 4 groups as close as possible in their age distribution, and unfortunately, that was not possible. And this is very bad news for all the males in this room. Because what this means is that the control group, although they had hundreds, a few thousands of people in their database, they were not able to get their control group old enough. So another way of putting this is to say that from a certain age onwards, most males have some prostate problem. Because it was just impossible to get control patients sufficiently old. Sufficiently old, meaning as old as the cancer cases and the BPH cases. So you will see in the data that the control patients are still really younger than the other patients, than in the other groups. And that means that in all the analysis, so the models that I will show you next week, we will have to correct for age. You need to do a correction for age. So strictly speaking, there's only 4 groups you want to compare. You want to look at longitudinal evolutions in these 4 groups, a little bit similar to what we have done so far. But everything needs to be corrected for age because the 4 groups are not having the same age distribution, and you want to avoid that you just would conclude that there's differences between the groups just because there's age differences. So that's the complication, and that's why all these analyses will have to correct for these age differences. So, okay, so that's the context. So next week we will start from this data set. We will first look at the individual profiles, and then we will start to build a model, and you will see it's going to be a model with many parameters. Because we have 4 groups, it's not a very simple time evolution that we will have in the different groups, so we will automatically have many parameters. We also need to do corrections for age, so it's going to be a model with many parameters, and then it's even more important that we really think very carefully about how we parameterize this model and how we write down the model so that we really understand all the estimates that we get in our output. But that is something for next week.